lecture notes, and I haven't. Well, I've actually completed those for the 3 lectures before this, but not for this lecture yet. Most of this I sort of have in some form. I'm just sort of touching it up. But anyway, those will be putting on the, what is it, like the discrete math page?
Yeah, so I'm going to put this PDF file into the discrete math website, seminar website on his announcement.
So those will, as I say, it's not quite done yet, but it'll be done before I leave. So it'll be done the next couple of days. Right, so this is my last lecture, and what I'd like to do today is kind of come back to graphs. So I'm a graph theorist, although I've been, I like doing this stuff, but secretly I like thinking about graphs more. And but also secretly a lot of the stuff that I've been doing is almost graph theory anyway. And I'd like to start today by making that connection apparent. So if you remember, really what I consider the main driver that made Cauchy-Davenport work was that if G is a group and I give you 2 subsets, then the intersection plus the union is always a subset of A plus B, assuming things are abelian here. Right, that sort of, it's a kind of submodularity property. That's what made Cauchy-Davenport work. So today what I want to do, I'm going to start off just on graphs. So we're just really going to move to the world of graph theory, and I'll be talking about some, very classical concepts, namely connectivity in graphs. Only I'm not going to be looking at all graphs. I'll be looking at some highly symmetric ones. And we'll see how connectivity in highly symmetric graphs relates to this. So that's sort of the goal for the first hour. So as I say, we're gonna really move to graphs in the beginning. It's not going to look too much like groups, but slowly over the course of the first hour here, it's going to basically transform into Cauchy-Davenport again. So we'll see that these 2 concepts really are one and the same. And then in the second hour, I'll be doing, I'll be talking about a very interesting theorem due to Shriver and Seymour, which is sort of like kind of like an Erdős-Ginzburg-Ziv problem, but on a graph. Anyway, I'll get to that in an hour. And actually, I'm going to set this on the side as well. So I just want to go to the world of graphs. So my graphs are going to have to be gamma, because G is going to be a group. Now I'm going to be interested in graphs that are highly symmetric. And what I mean by that are graphs with a rich set of automorphisms. So let me formally define these things. So an automorphism, like generally speaking, an automorphism of a structure is a bijection from the structure to itself that preserves the properties. Right? So it's basically a symmetry for graphs. An automorphism of gamma is a bijection, say phi, from the vertices to itself, such that a pair of vertices u and v, well, u and v will be an edge if and only if their images are an edge. So let's say such that uv is an edge of the graph if and only if phi of u, phi of v is an edge. Right, so it's a bijection. You've mapped the vertices bijectively to themselves, and the edges go to edges. So like, for instance, if you imagine I have a cube here in front of me, I can take the cube and rotate it by 90 degrees, and that's going to give some mapping of the vertex set to the vertex set that maps edges to edges, and that would be an automorphism. Gamma is vertex-transitive, if for any pair of vertices u and v, there's an automorphism sending u to v. If for all u, v, and v, there is an automorphism sending u to v. Right? So if you have a cube, then of course you can take the cube and rotate it about to bring any vertex to any other vertex, and that means the cube is going to be a vertex-transitive graph. Of course, if you have a graph that's vertex-transitive, then really it looks the same from every vertex, right? I mean, if you draw the graph on the blackboard, and this is the vertex u, then what this property means is that, well, for any other vertex in the graph, you could put v in the same position and fill in the labels and have another drawing through your graph, right? So the graph is somehow the same from every side. So there's a rich source of vertex-transitive graphs that we get from groups. So here, G is always a group, and B is just some subset. The Cayley graph on gamma generated by B. This is a graph with vertex set G. Oh my gosh. Yeah, this is hard for me. So this is a graph with vertex set G, and the rule is that you're going to have an edge. Oh, I should say this is a digraph. It's going to be a directed graph. So the rule is you have an edge from U to V. Now U and V will both be elements of the group G. You're going to have an edge from U to V if you can get from U to V by right multiplying by something in the set B. So U comma V is an edge if you can get from U to V by multiplying by something in B on the right. So I can express that like this. If V is an element of...
require B to be a set of generators.
No, it could... I mean, if B is not a set of generators, then this graph can be disconnected. Would be disconnected, yeah.
Allow for this.
Yeah, it's maybe an unfortunate choice of... The common thing is to call this the generating set of the Cayley graph, even though it's not actually a generating set of the group. Yeah, because you can let it be... Anyway, for our purposes, it doesn't. I mean, I'm not going to insist it actually be a generating set, but in the interesting cases, it would be.
So B is just a subset of G? Right?
Yeah, B is a subset of the group G. Oh, and now I seem to be working multiplicatively. Let me do this multiplicatively. I guess I'd like to define. For our purposes, we're mostly going to stay in abelian groups, but it's nice to define this in general groups. So let me do so. So G will be a multiplicative group, and UV is an edge if and only if V is in U times B. And the point is that so an instance is Cayley of, say, Z mod 2 to the 3 together with the set 0, 0, 1, 0, 1, 0, 1, 0, 0. This is, of course, the cube.
Vertex, the Cayley graph is group element. Group. Vertex set of Cayley graph is group.
Yes, the vertex set is always the group. Yeah. Yeah. So here the vertices are just the binary triples, right? And two of them are adjacent if and only if they differ in one coordinate. All right. So that's precisely what you know as the cube.
Arrows, digraph.
So okay, that's right. So I suppose this is sort of arrows both ways as I've defined it, but So the yeah, I mean, I guess I'm going to work a bit with graphs, a bit with digraphs today. So I mean, this definition would be the same if I say digraph, then you just need this to be an ordered pair. Oh, right. The key thing is that Cayley graphs are vertex-transitive graphs. Right? What's the point? So, I mean, this is a nice thing that if you have a group element and you want to multiply by something, you can multiply either on the left or on the right. Right? There are two sides. And here we've defined what it means to be adjacent in terms of right multiplication. Right? What it means for there to be this edge from u to v is defined in terms of right multiplication. Because of that, the group will naturally act on this on the left. So the map for every group element, the map that sends each vertex u to g times u is an automorphism of my Cayley graph. Right? If you take everybody in the group and just multiply on the left by some fixed element, well then if I had a pair of vertices uv that formed an edge before, that meant they satisfied this relation. Well, they satisfy this relation if and only if they satisfy it where I multiply each thing on the left by g. Right? So that tells me that uv is an edge if and only if gv is an edge, and that's precisely what we need. So vertex-transitive graphs are kind of a generalization of Cayley graphs, and you can see that Cayley graphs are really sort of incorporating the group structure in a nice way, right? A Cayley graph comes by taking a set B, and it's kind of encoding what it means to multiply an element by something in that set B. So, so many of the problems that we looked at in the additive number theory setting can translate into this kind of Cayley graph setting, and even more generally, we can think about vertex-transitive graphs. So vertex-transitive graphs are kind of a more general setting, and that's what I'm going to look to here at the start. So. So when you think about a vertex-transitive graph, you think about a nice, kind of symmetric object, right? And symmetric objects don't tend to have sort of bottlenecks. I'm not sure what I'm drawing right now, but it's not a very highly symmetric thing, right? There's a sort of bottleneck here, and so generally speaking, you'd expect if I gave you a nice vertex-transitive graph that it should be fairly well connected. Well, assuming it was connected to begin with, you wouldn't expect it to have a bottleneck like this. And that's what I'm going to look to. So, so I'm going to look toward results that say vertex-transitive and connected imply somehow well connected. Yeah, this is not a. Well, we'll be making this precise in a moment. I want to make this precise in a number of different ways. So I mean, this is the sort of general class of results I'm focusing on. So a structure that's. I mean, and in fact, this is true more generally than vertex-transitive graphs. I mean, if you have some structure that's somehow connected and highly symmetric, then you'd expect it not to have little bottlenecks, and this is what we should expect in the world of vertex-transitive graphs. So there's a nice theorem due to Mater that tells us exactly what happens for the edge connectivity of a vertex-transitive graph. Oh, I mean, maybe I should say what edge connectivity is. So, I mean, you know what it means for a graph to be connected. A graph is k edge connected. If, however, you delete fewer than k edges, it's still connected, right? And the edge connectivity of a graph, that's the size of that smallest set of edges you can delete to make it disconnected. So Motter's theorem tells us that if gamma is finite, vertex transitive, and connected, of degree d, then gamma has edge connectivity d. Right? So for instance, this graph maybe I should emphasize here that this is a graph, not digraph. Right, so you could, the way I've described this here, I guess technically it should have arrows going both ways, but you could just turn it into a graph. Replace those double arrows by single edges. So this is a nice, finite, vertex-transitive graph. It's connected and it's of degree 3, right? Every vertex has degree 3. And this is telling us that the edge connectivity of this graph is 3. The edge connectivity certainly can't be larger than 3, because you can always chop off all the edges incident with a vertex and you've disconnected the graph. Right, so if I tell you a graph is D regular, the highest the edge connectivity could possibly be is D. Motter's telling us that we always hit that. Yeah.
So this connected graph of degree D means...
So degree is the degree.
Oh, the degree of every vertex. You know,
Vertex-transitive is a regular graph.
Yeah, I glossed over that. It would have been good to say. That's right. Right, this vertex transitivity forces the graph to be regular, right? Because for any two vertices, there's an automorphism that carries one to the other. There's a bijection on the graph, right? So it maps this vertex to that vertex and happens to map the neighbors of this one bijectively to the neighbors of that one. So in particular, any vertex transitive graph is going to be a regular graph.
Then
Yeah.
degree D in digraph is defined by the sum of the out degree and the
Let's not worry about degree in digraph. Let's stay in graph now. Yeah, sorry. I do want to jump back and forth between graph and digraph because I sort of need to get the connection to additive number theory. But let me not worry about degree in digraphs for the moment. Okay, is everybody happy with the statement? Was that obviously false? Actually, it is false if you drop the assumption finite. Can you think of a deregular infinite graph that's connected and vertex transitive, but is not well edge connected?
Well, take a K graph of some infinite group.
There exists a group which is probably a successful answer to that. There's kind of an easy one.
What is the edge connected? This means the minimum number.
Yeah,
you're saying it cannot be higher. Of course, the degree is D.
Right. So it can't be higher than D because you can always split one vertex off of the rest by deleting those edges incident with it. So the claim is there's no other edge cut that's smaller.
And then you say
That's right. So there's an infinite deregular tree, right? This is how you make one when D is 4. Right? You just keep going. That's a perfectly good infinite vertex transitive graph. It's going to be 4 regular in this case and connected. And this actually is edge connectivity 1. Right? You delete any edge and you've broken it into 2 pieces. So this statement fails for infinite groups. But it's true for finite ones. And so we're going to do the proof of this now. And I guess I want you to recognize that the proof is sort of running along the same lines as this. Let me actually just make a couple notes here. So if I give you a graph and a subset of vertices, I'm going to let D of A denote the number of edges that have one end in A and the other end in the complement of A. So it's the number of edges that have exactly one end, right? So if here's my set A, here's the complement of A. You've got some number of edges here. The number of those is D of A. That's the size of the edge cut. So you'll note that D of A is the same as D of the complement of A. Right. The more interesting property that holds true is the following. D of A intersect B plus D of A union B is always less than or equal to D of A plus D of B. And, well, now we're indeed noticing something that looks the same as before. Right? This is a very easy property. I will prove it with a quick Venn diagram. So this is a Venn diagram. I'm going to partition this is the vertices of the graph are what I'm splitting into these sets here. On the left, you see A. On the right, you see V without A. On the top, you see B. On the bottom, you see V without B. Right? So D of A is counting the edges that cross from left to right. D of B is counting the edges that cross top to bottom. D of A intersect B is going to be the edges that cross this cut. And D of A union B, the set of edges that cross this one. Right? Now for the purposes of this picture, you don't have many different types of interesting edges. I mean, an edge that has both endpoints in the same block here doesn't contribute to any of these. You've got some edges that cross vertically and horizontally, and then some edges that cross diagonally. You'll see that when I add up D of A plus D of B, what do I count? I count each yellow edge once and each pink edge twice. Right? So D of A counts it counts these edges here, but it counts the edges of this type plus the edges of this type plus the diagonals. So it counts that number of edges in D of A. D of B counts the edges like this and also the diagonal edges. So the sum of these two counts all of the yellow edges once and all the pink edges twice. D of A intersect B, that counts these edges once, and these edges once. D of A union B, that counts, these edges once, and these edges once. So in fact, this is true, and in fact, moreover, the difference is twice the number of edges that go between there. Right? It's a fairly it's a fairly simple property, and it's a fairly important one. That's what we're going to focus, or we're going to take advantage of this kind of uncrossing process, just as we did for Cauchy-Davenport with subsets of a group. We'll now work with subsets of a graph and do the same. So let's prove Mater's theorem. So here's what I'm going to do. I'm going to choose a subset of vertices A, so that D of A is as small as can be. But I want A to be no fair choosing the empty set. I'm also going to insist that A be at most half the vertices in the group, in the graph. So I'm going to choose a subset of vertices that's at most half. let me say with, such that 1. Now I'm going to try and optimize my set in 2 ways. First criteria, I want d of a to be minimum. Second priority is I'd like for the set A itself to be as small as possible. But I mean this subject to the first constraint. So in other words, my over all sets A, whose size is at most half, for which d of a is minimum, I'm going to choose one where the size of A itself is minimum. I'm going to focus on that. And let me just note, this set A, I mean, this constraint is not really a serious one, right? We will have picked up a set A so that d of a is as small as possible. Because for any set, either it or its complement would have size at most a half. So we haven't lost any serious generality with this assumption. Now,
why isn't A usually going to just be a vertex?
It is usually going to be vertex. I'm just trying to prove, I mean, my goal here is just to prove that we have edge connectivity D. So if it was a vertex, then I have 1, right? That's right. And you're absolutely right. Generically, I mean, if you think about a vertex-transitive graph, you think about the cube or something, you only get a vertex almost.
Condition 1 is going to tell you to pick a vertex.
Yeah, just about every time. Yeah. Well, in fact, I mean, if the theorem's true, then the vertex is, in fact, the answer. Yeah. But this minimization gives us some clean way to go down and prove that that's the truth. So first, let's suppose there exists an automorphism such that when you look at phi of A intersect A, phi of A intersect A is a proper non-empty subset of A, right? So what's happened here is here's your set A. I can apply some automorphism so that set phi of A overlaps with the first but is not equal to it. Well, if that happened, then we can take advantage of this business, right? Let's just consider d of A intersect phi of A plus d of A union phi of A. Well, that's got to be less than or equal to d of A plus d of phi of A. Well, d of phi of A is the same as d of A, right? I mean, this is just an automorphism. So the number of edges sticking out of A is the same as the number of sticking out of phi of A. So this is just twice d of A. And d of A is the smallest possible value of D over all sets which are not empty or everything. That last criteria we have to be a little bit careful about. Right? I mean, if you take the function D and evaluate it at either the empty set or the whole vertex set, then you get 0. But the good news is that neither of these sets is going to be empty or the whole thing. A intersect phi of A certainly is not going to be the whole thing, and it can't be empty because I'm assuming just by our assumption. How about A union phi of A? Well, it certainly won't be empty. Could it equal everything? Well, no. A and phi of A are both at most half the vertices, and they do overlap. Right? So that means their union is not everything. So this set is not everything. So these two sets are proper non-empty subsets of vertices, and that means that their D value must be the same as this plus this is less than or equal to twice D of A, but D of A is the minimum over all the proper non-empty subsets. So in fact, D of A intersect phi of A must equal D of A union phi of A, which equals D of A. But then we get a contradiction to this second criteria. Then we could have replaced the set A by A intersect phi of A. See that I'm really working right to left here now. Well, so be it. So what do I know? We got a contradiction here. Right, so there's no automorphism that takes the set A and maps it to a new set with a proper non-empty intersection with the original. There's a name for this property. It's significant. A set with this property is called a block of imprimitivity. But for our purposes, it's not so important. Here's the key point. Suppose you have two vertices u and v in the set A. You could choose an automorphism that maps u to v. Right? So here's my set A. I mean, my graph is vertex transitive, so there exists some automorphism that maps u to v. Now, if you look, that's going to map the set A to some new set phi of A, which will intersect A. Right? Because I mean, they'll both contain v. And we know that anytime you've found an automorphism phi so that phi of A intersects A, then phi of A equals A. So what we've got right now is if phi is an automorphism and phi of A intersect A is not empty, then phi of A equals A. Right? So if you chose an automorphism phi that maps u to v, it has to map this set A right back to itself. Right? So every automorphism mapping u to v, let me say, fixes A as a set. When I say that, I don't mean you have to fix every point of A. I just mean the set of elements A has to map back to A. All right? So if I take two vertices here, u and v, there's some automorphism that maps u to v. That automorphism has to map this whole set A back to itself. Now, what good is that? Well, u has degree d. I can split that degree into two parts. It has some neighbors inside the set A and some neighbors outside the set A. Right? Let's suppose that u has, let's say it has A neighbors inside and B neighbors outside. Well, what we've just said is every automorphism mapping u to v maps the set A back to itself. So what that means is that when u goes to v, these other vertices here, they're going to go to other vertices inside the set A, and these other vertices go to other vertices outside the set A. And so that means that the vertex v has also got to have B neighbors outside and A neighbors inside. Right? So this property, I mean, together with the vertex transitivity and this property, tells us that, in fact, there exist numbers A and B such that every vertex in A has A neighbors inside A and B neighbors outside. Right? So again, the thing that we know is every automorphism that sends u to v has to fix this set A as a set, and that tells us that any two vertices in that set A kind of look the same, and the the sense that they have the same number of neighbors on the inside and neighbors on the outside. And now we're in a position where we can just, now we can just count the number of edges sticking out of this set. Right? So what do we know here? Well, we know, by definition, A plus B is going to equal D. But in fact, I can just get a good bound on the number of edges sticking out of the set. Oh, let me note as well that, B can't be 0. A is not the whole graph. If B was 0, then this graph would be disconnected. It is not. It's in this list of assumptions somewhere back here, right? My graph is connected, so B is not 0. So that's what I've got. Now, how large is D of A? Well, this is exactly equal to B times the size of A. How large is the size of A? Well, the size of A is at least little a plus 1. Right? For every vertex here, you've got it plus its A neighbors that are in this set. Right? For any vertex in that set A, it and its A neighbors are a disjoint set. Those are A plus 1 vertices. So the size of B plus A is at least this, and you can see this is at least, well, this is BA plus B, and B is at least 1, so this is at least A plus B, which equals D. Right? So that's it. I see one or two looks of some confusion. There wasn't. The only thing that happened here is I bounded the size of A by this, and then everything else is just algebra or just manipulation. So what we've learned is that in fact this set A, because of this sort of symmetry property, every vertex has to look the same, and then that forces you to have a lot of edges sticking out of this sort of set. In fact, you can do a little bit more work using the same kind of uncrossing principle and work out what the structure of all of the edge cuts of size D in a graph of this form could possibly look like. It's pretty hard to have even just one. In fact, there are really only a couple cases. You could have a graph that's a cycle. Then you see this graph, its edge connectivity is 2, but any 2 edges that you delete disconnect the graph. The other main example of a graph which hits this bound in an interesting way, meaning not just for a single vertex, is you can take you can construct a graph which looks like complete graphs of order D with one edge sticking out of each vertex. And you can join these together. And this is the other sort of essential class. And this is corresponding over here to the case where you're hitting this thing with equality because B equals 1. And
What is the graph? Complete graph?
yeah, sorry, I didn't say this. Let me do something more, maybe a little bit more explicit. Let me take I need a graph that's arc transitive is kind of the point. So you could, for instance, take the Peterson graph and and then replace each vertex by a triangle in the following form. Now, so you have to do that at every vertex. Now, the Peterson graph is very symmetric. It's very highly very highly symmetric. So in fact, the Peterson graph, you could take any edge and any other edge and map this one to that one and in the orientation you like. So that's called being arc transitive. And the fact that this graph is arc transitive implies, I mean, there's something to check here, but it implies that when you replace each vertex by a little complete graph with just one, so the incoming edges will be joined one-to-one to the vertices of this complete graph. When you do this process, you'll now have a vertex-transitive graph, and this now has some more interesting d-edge cuts. Okay, let me keep moving and talk about. Let's keep moving. So I wanted to say this in a couple different forms. I'd like to do one in terms of, let's talk about vertex connectivity. So same assumptions. So throughout here, I'm going to be looking at connected, deregular, connected, vertex-transitive graphs that are finite. And so there are a couple nice theorems. So there's a theorem due to Motter and Watkins. These are separate. That says that if G satisfies these properties, is deregular, and satisfies star, then its vertex connectivity is at least 2/3 d plus 1. So if I give you a connected finite vertex-transitive graph that's deregular, then the vertex connectivity is always at least 2/3 d plus 1. Let me show you the tight instance for that guy. So you take a whole bunch of complete graphs.
Maybe you want to explain what vertex connectivity?
Oh, maybe I should explain what vertex connectivity is. Yeah, why don't I explain what vertex connectivity is? So, I should say, for my purposes, I don't like complete graphs. No graphs are complete. I mean, you have to be careful when you're defining vertex connectivity for complete graphs, right? Because if you take a complete graph, no matter how many vertices you delete, it's still connected. So don't worry about that. So graphs aren't complete. For graphs that are not complete, the vertex connectivity is the smallest number of vertices you have to delete to get a disconnected graph. Right. So I'm going to construct here a vertex-transitive graph by taking a whole bunch of copies of Kn, and I join each one completely. So they're in a cyclic order here, and I join each one completely to the one before it and the one after it. Now, what's the degree of this graph? This will be a vertex-transitive graph. It's pretty trivial to see that. The degree here, d, would equal what? Well, each vertex is joined to n guys here and n guys here and n minus 1 here. So the degree of this graph is 3n minus 1. But you can see that it has sets of size 2n that disconnect it. Right? If I take two of these sets and delete them, I'm going to disconnect the graph. So the vertex connectivity of this is is 2n, so it hits this bound, making this theorem tight. So for a vertex-transitive graph, the connectivity is always at least 2/3 the degree. There's a similar theorem of Hamidun, which works for digraphs. So this is going to be a D outregular digraph satisfying star. its vertex connectivity is at least 1/2 d plus 1. And now I need to tell you what vertex connectivity means for a digraph. Well, it's basically the same. We say that a directed graph is strongly connected if for any two vertices there's a directed walk from one to the other. Right? The vertex connectivity of a not complete digraph is the smallest number of vertices you can delete, so there's no directed path between some pair of vertices. And in fact, the example here is very similar to this guy. What you do is you make this complete graph, you add edges both ways in each of these. So these are sort of bidirected complete graphs. And then you direct these edges all the same, all consistently like this. Now what happens? Well, now if you look at a vertex, its out degree is going to be what? Well, it's joined to these n vertices and n minus 1 here. But if you just delete one of these blocks, right? If I just delete this block, I can no longer get from this vertex to that one. Right? You can only kind of go clockwise around this cycle. So the vertex connectivity of this graph is in fact equal to n. And that shows that this guy's tight. Okay, so we've got some theorems saying these sorts of things. Yeah, let me just stay in the same vein and tell you another one. Right, so these are kind of like lower bound theorems, right? They're telling you, you give me a vertex-transitive graph and it's degree d, then there's some sort of natural lower bound on how well connected this could be. That's like a lower bound theorem for a sumset problem. Another thing you might like to do is you might like to sort of characterize what small separations look like in vertex-transitive graphs. And so there is a theorem of this form due to me and Boy and Mohar. And I'm going to say it I'm not going to say it in the sharpest possible form here, but here's the game. We're now going to look at a sort of small cut set. Let me add just one bit of notation. Yeah. So if I give you a graph and I give you a subset of vertices A, then the neighbors of A, this is going to be the set of all vertices that are not in A, but are adjacent to someone in A. Okay, so that's the neighbor set of A. Actually, let me go ahead and take one more step and make an observation. If you think about deleting some set of vertices and disconnecting the graph, right? You could take A to be one of the components of that disconnected graph, right? And then the neighbor set of A would just be a subset of the vertices you deleted, right? So in fact, finding a small set that disconnects the graph is really the same as finding a set A so that its neighbor set is small and A union the neighbor set is not the whole graph, right? So let me. Sorry, that may have been overly confusing. Let me just write a simple statement. Observation, so saying the graph gamma is k-connected, this is equivalent to saying that for every subset of vertices, either A together with its neighbors is the whole vertex set, or the size of the neighbor set of A is at least k. Right, so saying your graph is connected, it's just saying that, for any set of vertices you take, either this set together with its neighbor set is the whole graph, or the neighbor set has got to be size at least k.
You would say it's not empty.
Yeah, not empty. Thank you. Yeah, thank you. Yeah, you have to worry about it. You really do have to worry about hitting the bottom and hitting the top all the time in this business. It will really spoil a theorem every once in a while if you aren't careful. Anyway, so so the theorems I stated here so far are kind of lower bound theorems. I'd like to state a kind of structure type theorem. So so here gamma is vertex transitive. And actually, for this, gamma could even be finite, but I want it to be, the degrees of vertices should be finite. So the graph would be allowed to be infinite as long as the vertex degrees are finite. Here A is going to be a subset of vertices of gamma, and the size of the neighbor set of A, and it's got to be the size of A has got to be not too large. So this is at most some constant times the size of the whole of the whole vertex set. So let's I guess let me assume the graph is actually finite. So if I give you a vertex-transitive graph and a set of vertices that's not too large, and the size of the neighbor set of A equals k. So you have some set of vertices where the boundary has some fixed size k. Then one of the following holds. So I mean, how can you do this? How can you have a sort of set of vertices that only have a neighbor set of size k? So k is, imagine k is some small thing. Well, one thing you could do is your set A itself might be fairly small. That's certainly possible. It could be that the size of A is at most some function of k, and this is cubic, the truth is probably like quadratic, but f of k, in fact, let me say it that way. The A is at most some constant times some other constant, say c prime times k cubed.
Doesn't it depend on c?
No, these are two. There's no dependence of these two. Yeah, there's no dependence on those. Sorry, I didn't actually look up the paper. It's like 100 or something. Like it's not even a terrible number. But sort of morally, one reason that you might have a set with a sort of small boundary is that your set itself might be small. The other reason is that your graph. The other reason is sort of like some kind of like a linear structure. right? Same thing, it's like an arithmetic progression-y type thing, some sort of linear structure. If your graph has an essentially cyclic structure, then you can find some small sets. So the other possibility, and this I'm not going to say precisely, is there's remember that block of imprimitivity? So it's a set of vertices so that however you map it around, it either is disjoint from the original or overlaps. So you have, anytime you have one of those, you can look at all of its images under the automorphism group, and they partition the vertices. Right? I mean, again, you couldn't have two of them intersecting because then you would have seen that back at the start. So the other possibility is that there's a cyclic sequence of blocks of imprimitivity. This is actually a system of imprimitivity. So you take one of those and all of its images. So there's a cyclic ordering of those, and each of these guys has small size, and all of the edges only go a bounded distance relative to the cyclic ordering. And in that case, so you can make vertex-transitive graphs of this form. Like even that clique-like thing that we saw over here was an instance, right? Another thing you could do is, instead of just adding edges between consecutive pairs, add edges between guys at distance 2, right? This would be a graph that's nice and vertex-transitive, but has some small cut sets that separate lots of vertices. And effectively, what we're saying here is that, in fact, if you see that in general, that's more or less what your graph looks like. So gamma has a system of imprimitivity with blocks of size less than k, and such that all edges has a, let's say, a cyclic system of imprimitivity. So you've got these your vertex set chops up into blocks like this, and every automorphism just moves around whole blocks to blocks. And the blocks are small in size, and all edges jump at most length k with respect to this cyclic ordering. Okay, so you can make a variety of vertex-transitive graphs in this manner. And if you do that...
And what is A here? It's a set of consecutive blocks or something?
Yeah, well, right. Actually, so I didn't actually say what A is. Right, A is roughly going to be some kind of interval of blocks. That's right. Yeah, so the main structures here are it really is just that. It's really just a kind of generalization of this. So if you take a slightly rougher version of this, you can take kind of an interval of these blocks and then delete some vertices out here, and you'll see a small cut set that separates a lot of graph from a lot of graph. And really that's the only way you can really do it. Okay, so that I didn't even manage to say that precisely, and it took more time than I wanted. Let me. Okay, let's hold on to our chairs for a moment. I'll make this hour go a little slightly longer than an hour, and the next one will be slightly short. I want to bring this back to vertex-transitive graphs, or back to additive number theory, and. And so what I want to lead toward is really just reinterpreting Cauchy-Davenport in this setting. And in fact, that's quite easy. Okay. If I made this a digraph, then I'll declare n plus of A to be the set of vertices such that there's an edge from something in A to something to V. Let me say there exists U comma V in E such that U is in A. Right, so just switching perspective to digraphs now, I'll call this the out neighbors. So I give you some set of vertices A. The out neighbors are all the vertices that are not in A, but you can get to by following an edge forward out of A. And now a digraph, gamma is going to be k-connected if for every subset of vertices either A together with its out neighbors is the whole, or the set of out neighbors has size at least k. Right? This is same property as before. If you have some set of vertices here and its out neighbor set has size k, then when you delete them, you can no longer get from A to any of the rest of the graph. Right? And conversely, if there was some set of k vertices so that when you delete, the graph is no longer strongly connected, then there is some component that looks like this. Right? So sort of saying that your directed graph is well connected means that all of these out neighborhoods, means that whenever you look at this sort of vertex out neighborhood, either this set together with it is the whole graph, or that out neighborhood is large. Now let's think about what that means in Cayley graphs. So if I give you this Cayley digraph now, so my vertices are the group elements in G. B is telling me where the edges are, right? You have an edge joining U to V if you can get from U to V by adding something in B. Now, what is the n plus of A? Right, if I give you some subset of vertices, n plus of A, those are all the vertices that you can reach by taking something in A and adding B to it. Right? So this is precisely the set. Sorry, I can even do it in set notation. This is all the vertices you can get to by starting in A and adding in B, except not those ones that were already in A.
Now you're using additive notation.
Yeah, sorry. Now I switched to additive notation. Yeah. I hope that's not tripping you up too much. I mean, yeah, I mean, the introduction of multiplicative notation was maybe only to emphasize that Cayley graphs work for them and that symmetry you always have. For my purposes now, I wanted to work additively. I'm headed toward Cauchy-Davenport, actually. All right, so for a Cayley graph, the out neighbor set is just this. It's all the vertices in A plus B without A. So let's now just restate Cauchy-Davenport. So the way Cauchy-Davenport was usually stated, A and B are subsets of the integers mod p. Here p is prime. And I gave you some bound on the size of their sumset. Now, I'm going to toss in a couple of added conditions just to make this set of equivalences look right. But you'll see that these added conditions don't really affect much. I'm going to assume the size of B is at least 2. You know, that's not really a serious assumption. When B has size 1, you know that the size of A plus B is the size of A. Another thing I'm kind of free to assume for the purposes of Cauchy-Davenport is that the set B contains 0, right? Because you can always take the set B and shift it so that it contains 0, and it doesn't affect the sumset. So I'm going to assume as well that 0 is in B, and I'm going to set B prime to be B without 0. Okay, so now I'm just going to write down some statements that are equivalent to Cauchy-Davenport. So these assumptions were really not significant for the purposes of Cauchy-Davenport. The main statement, or the general one, is that the size of the sumset is at least the min of P and the size of A plus the size of B minus 1. Now, an equivalent way of saying that is either A plus B is equal to the whole group, or the size of A plus the size of B is at least, oh, sorry, let me write this a little differently. Well, I mean, I could, you see, the set A plus B, it will definitely contain all of A, because B has 0 in it. Right? So instead of telling you the size of A plus B is at least this, I could throw out all of the elements of A. So another way of saying this is size of A plus B without A is at least size of B minus 1. Right? That's just equivalent to this. So when you add up these two things, either you get the whole group, or when you take that sumset certainly contains all of A, and when you throw out that portion, what's left is at least size of B minus 1. Okay, I'm just going to go very slowly. I'm going to restate that using B prime. Either A together with A plus B prime is the whole group. That's just the same. Or the size of A plus B prime without A is at least the size of B prime. Right, so either A together with, I mean, this condition's just the same as this. A plus B is the same as this set. And over here, well, A plus B without A is the same as A plus B prime without A. Those two sets are the same. But what is this last condition? This last condition says in the Cayley graph on ZP generated by B prime, what does this say? So A union this, well, this is the neighbor set of A. Sorry, this is saying A together with its neighbors. Let me just, either A together with the neighbors of A is equal to the whole graph, the whole vertex set, or this is the size of the neighbor set. The size of the neighbor set of A is at least the size of B prime. That's just saying that this Cayley graph has connectivity equal to the size of B prime, equal to its out degree. So the big upshot here is Cauchy-Davenport is equivalent to the statement that every simple Cayley graph on ZP maybe I should say digraph. Here, P is prime, has connectivity equal to its out degree. Right, so just like Motter's theorem was telling us, if I give you a vertex-transitive deregular finite connected graph, then the edge connectivity is equal to the degree. The Cauchy-Davenport we can interpret just as being a statement purely about connectivity of Cayley digraphs on ZP. So if you take any Cayley digraph on ZP, where P is prime, then the vertex connectivity of this directed graph is equal to its out degree. And that's just this translation over here. And it's just equivalent to Cauchy-Davenport. So So by way of Cayley graphs, there's really an intimate connection here between lower bounds on sumsets and connectivity of these Cayley graphs, and more generally connectivity of vertex-transitive graphs. Okay, so let's take ourselves a good 10-minute break, and we'll pick up with a different side of graph theory and additive combinatorics when we come back.